Welcome to the MIPS Assembly Language section of the MIPS Software Training course. In this section, I will cover the usage and conventions for the 32 general purpose registers, synthesized instructions, assembler optimizations, common macros that you can use, and calling conventions. There are conventions for register usage and naming that will be used by compilers and debuggers. When you are coding in assembly, it can be easier to understand your code if you use the common software names for the registers. You can define these yourself, or you can include the file mipsregdef.h in the beginning of your code. Here are the register conventions. 0 is a constant 0. It can be read or written, but will always read as zeros. It's not really a convention because you really can't use it for anything else. The AT register is reserved for synthetic or macro instructions generated by the assembler. There is an assembler directive to stop it being used by the assembler called .noat, but using this could make macros take longer. Registers V0 and V1 are used for a function call return values. Registers A0 through A3 are used for passing arguments to a function. More on this later in the section. Registers T0 through T9 are temporary registers and are not guaranteed to survive a function call. So, if the caller is using them, he must save them on the stack before calling a function. S0 through S8 are the saved registers. These are guaranteed to survive a function call because the called function must save them if it intends to use them. K0 and K1 are kernel registers. These are used by the kernel mostly for the first part of exception and interrupt processing. So if you're using an OS, your program should never use these registers. GP is used as a global pointer. It'll point to a location that is determined when your application is initialized. This location will be in the midst of your static data section. Loads and stores to data lying within 32 KB of either side of the global pointer can be performed in a single instruction using GP as the base register. This is used differently for the Linux OS. More details on how it is used in Linux will be covered in the Linux section. GP should be saved by the calling function. SP is the stack pointer and must be preserved by the function being called. FP is the frame pointer, which is used by some languages for functions that need to create dynamic variables. In this case, the frame pointer is used to save the incoming value of the stack pointer, so the function is free to change the stack pointer. Note, the frame pointer is also known as S8, which is one of the mandatory save registers that a called function must preserve. RA is the return address register, which, as you have seen in the MIPS instruction section, holds the return address stored using a jump and link instruction. This register must be saved on the stack before another function is called, and you cannot use it for anything else. As you have seen in the MIPS instruction section, the assembler adds macro instructions to complete the instruction set available to you. The assembler creates these from machine instructions. They are also used to cover up obscurity. For example, the divide instruction also includes a check for divide by 0. As you can see here, it helps to simplify the task for loading immediate values. The assembler allows you to write code that is more simplified. I'll show you some simplified instructions that you can write and what the assembler translates them into. For example, if the offset is 0, you can simplify your code by omitting the offset. For a register offset, You can let the assembler do the arithmetic for you. As you can load an immediate data value, you can also load an immediate address value. The assembler will break the address down into the high and low order bit pieces using multiple instructions and do the load. And you can use a register offset greater than 16 bits. In this example, the assembler will break the offset down into the high and low order 16-bit pieces using multiple instructions and then store the value. Note, when the assembler sees the constructs %high and %low, it will convert the high or low 16 bits of the 32-bit immediate value and correctly adjust the resulting half words with the proper sign extension. It will also simplify the writing of immediate values that are larger than 16 bits. For example, in using the add unsigned instruction, it is straightforward when using a 16-bit value. The assembler makes it just as easy to use immediate values that are larger than 16 bits and converts the one instruction to 3 to do the job. The assembler will optimize your code by filling in the load, branch, and jump delay slots with an appropriate instruction when it can find one. This will cause the disassembly to look different than the code you have written. You can control some of the optimizations through the use of the .set directive. The assembler defaults to reorder, which means it will control the instructions in the branch and jump delay slots. It will also move instructions around to avoid load delay stalls. If you want to hand tune some of your code, you can tell the assembler to leave it alone by placing the .set no reorder directive at the start of the code you don't want touched, and then resume optimizations by using the .set reorder directive when you want it to start optimizing again. Sometimes you may have a section of code that you don't want loads or stores reordered or removed altogether because you are reading or writing a device register or other volatile memory locations. You can tell the assembler not to optimize loads and stores by starting the section of code with the .set volatile directive and then use the .set no volatile when you want loads and store optimization to continue. If you find you need to use the assembler temporary register in a section of code, you can have the assembler give you an error when it needs the AT register for a macro by setting .no AT directive. You can resume the use of AT for macros by setting the .set AT directive. When you are tuning your code, you may want the assembler to use all optimizations, but warn you when it had to generate more code due to macro expansion. You can do that by using the .set no macro directive. A function that does not call another function is called a leaf function. You can also think of this as a dead-end function because it goes nowhere else. There is very little overhead needed for a leaf function. Since you're not making any function calls, you only need to worry about preserving the registers you actually use. For example, in a leaf function, you don't have to worry about saving the arguments or the save registers because you usually can get by with using the temporary registers. You can use the stack for storage as long as you preserve the stack pointer. Remember to leave the return address in the RA register and return directly to it. There are several code macros you can use in the .asm.h include file. One of them is this convenient macro for leaf functions. Let me explain what it does. First, the .text directive tells the assembler to put the code in the text section of the object file. The text section is normally where the assembler puts the machine instructions. The .globl places the name of the function in the symbol table, which makes the symbol name globally visible to the linker and available to any files that this file is linked with. The .ent has no effect on the code produced, but tells the assembler to mark this point as the beginning of the function called name, and to use that information in debug records. Name : labels this point in the assembler's output with this function's name and identifies the address that other functions will use to call this one. Another convenient macro is the end macro, which you can use at the end of an assembly function. It looks like this. The dot size makes it easy for the assembler to compute the total number of bytes the function uses and places the size with the corresponding function name in the symbol table. .end is used by debuggers to mark the end of the function. Up to this point, we have seen which registers need to be preserved from one function to another and where to find the current stack pointer and return address. I'll now turn your attention to argument passing. In order for your assembly code to be called and call other functions, you need to follow an agreed-upon convention. I have been using the O32 convention in this section to explain the register layout. I'll continue using it to explain the calling convention. The calling convention is designed to be compatible with how C functions call each other. To optimize argument passing, the O32 convention uses 4 general-purpose registers, A0 through A3, to pass arguments to any function. It still allocates stack space for these arguments, but does not actually copy the arguments from the argument registers to those locations. This space is allocated in case the called function will need to save the arguments to the stack. When your assembly code gets called, it can find its first arguments in the argument register and the rest in their expected locations on the stack. When your assembly call calls another function, it needs to save its arguments it was called with on the stack in their pre-allocated stack locations. Your function needs to place the arguments it is passing to the function it is calling in the argument registers and any overflow into a new stack frame. Let's see how this works in practice. Here I have a simple function called with 3 arguments. The first argument will be a pointer to a string and placed into argument register 0. The second argument is also a pointer to a string and placed in argument register 1. The third argument is an integer and it'll go into argument register 2. This was easy because we only had 3 arguments, and they all aligned to fit in the first 3 argument registers. Note, the stack pointer will point to the word reserved for the first argument, stack pointer plus 4 to the second, and stack pointer plus 8 to the third, but no data will be actually stored in these locations at this time. Now let's see what a more complicated function call would look like. Say your assembly code was going to call printf. Printf is a complicated example because not only are the number of arguments variable, but so is the size of the arguments. This makes for an example that is more illuminating. In this example, printf has 4 arguments. The first argument is the pointer to the format string. It goes into the A0 argument register. There is also room allocated on the stack for this argument in case the function being called needs to save it. Note, the stack pointer should be aligned to a double word boundary. Next is a floating point number of type double, which, for MIPS, that means 2 consecutive words aligned on a double word boundary. Since the stack pointer is aligned to a double word boundary, then to align this argument on the stack means skipping the next word to get the proper alignment. To keep everything even, you also need to skip the use of the A1 argument register. This all means that the second argument will be placed in the argument registers A2 and A3. Now we are out of registers to store arguments, so the next argument will be copied to the stack. It is also a double, and since we need to allocate space for the first 2 arguments, the double word will start at the new stack pointer plus 16. The last argument is an integer and will go on the stack at position stack pointer plus 24. We are now ready to look at a sample assembly function. This function will copy an input buffer to an output buffer with the assumption that the input and output buffers are word aligned and the number of bytes to copy is an even word number. First, I have included two files. The regdef.h file allows us to use register names such as A0 instead of register numbers, and asm.h contains the leaf and end macros. Next, I use the .set no reorder directive because I want to control the order of the code and the use of the branch delay slot. For the start of the function, I use the leaf macro with the name of the function to start things off. I'll compute the ending address of the input buffer by adding the length argument to the address of the buffer argument. Next, load the input data to the T0 register. Then, store it to the output buffer. And increment the input address. Now we're going to test to see if we're at the end of the copy and branch back to the line that is labeled 1 if we are not. While the branch address is being calculated, the branch delay slot will execute, so I use the slot to increment the output address. When the above branch is false and the input address equals the output address, the execution will fall through the branch and I will use the jump register instruction to return to the calling function. I have nothing for the jump delay slot, so I'll just put a no op there. Then I'm going to turn reordering back on so any code that follows will be optimized. And last, I'm going to use the end macro to show the end of the function.